Let's get some scratch paper here. So last time, what did we talk about, please?
Eigenvalues and eigenvectors.
Yes, eigenvalues and eigenvectors. That's exactly what we talked about. So what is the problem about, the eigenvalue problem? We're given a matrix A, and this time it's a square matrix, right? And what do we need to find? We use the same example I used in the other sections. Actually, the one from the slides will do. Okay, so how about 9200? So what is the problem of finding the eigenvalues? When do we say? Sorry?
Oh, like, are you asking like what the next step is to go from here to find this matrix's eigenvalues?
Yes, sure. That's exactly right. But what are the eigenvalues? What is it that we're looking for, most importantly?
We're looking for a vector that if we multiply it with the matrix A, is going to be equal to some number lambda times that vector.
Yes. So when you apply the matrix A, the transformation A to vector X, what comes out on the other side is parallel to the original vector X. It's exactly right. And as you just told us, the procedure for finding the eigenvalues and eigenvectors is to write down the matrix and find the eigenvalues first by writing down the characteristic polynomial that looks like this, right? So that's the determinant of A minus lambda I. And what's the determinant of A minus lambda I?
9 minus lambda negative lambda, or 9 minus lambda 2, 0, negative lambda.
Yes, that's exactly right.
I got a question about
yes.
At the top. Would it be wrong to say that the lambda is the scalar equivalent of the vector or of the matrix A, or would you just not say that?
Yes. So depending, what do you mean by the scalar equivalent of a matrix? So lambda is a number?
Yeah, I guess by equivalent, I just sort of mean that like when you multiply the vector X by lambda and A, you get the same result.
Yes.
So like you could say they're not the same, but they're equivalent. Yeah.
Yes, in that sense, you can, sure. But sure, that's exactly right. So lambda X is just a vector, right? That points in some direction. If lambda is negative, it points in the opposite to X direction. If lambda is positive, it points in the same direction. If lambda is 2, that X is stretched twice. If lambda is minus 1/2, then that X is shrunk twice and points in the opposite direction. And AX is just some vector that generally, under the influence of A, changes direction. But if there's a special vector X that stays on its own line after A is applied to it, then that is called A's own vector, or A's eigenvector, a vector that's characteristic to A. Okay, so let's find the characteristic polynomial. In this case, the matrix is small and it has a 0 there in just the right place for us to easily write down the determinant. So the determinant of this is going to be 9 minus lambda times minus lambda. Okay, so now the next step to finding the eigenvalues is to set the characteristic polynomial to 0 and solve for roots. Okay, so it follows that the roots of this are lambda equals 0 and lambda 2 is 9. So I have 2 roots. So in general, if you have an nth degree polynomial, you have n roots. Okay, sometimes some of the roots may be complex or repeated, but you will have n roots. So this is a nice case. The nicest case where you have roots that are distinct, that is, none of the roots repeat, and they're all real in this case. So one is 0, the other is 9, distinct roots. So good case. So now comes the time of finding the eigenspace associated with each eigenvalue. So what is eigenspace? For lambda. And we'll have a notation for eigenspace. We'll denote the eigenspace associated with the eigenvalue lambda by E sub lambda. So last time I used explicitly eigenvectors, and now I'm mentioning the term eigenspace, and that's on purpose. Okay, so in this case, where you have a 2x2 matrix, where the roots are distinct, each eigenvalue has a line of associated eigenvectors. So let's find the eigenvalue. It's a one-dimensional space. So let's see this. So let's take lambda1 equals 0. How do I solve for the eigenvector? How do I find the eigenvector associated with this? So 9 minus 0, 0, 0 minus 0. Okay, so I wrote down this as A minus lambda times I is this matrix here. What I'm looking for is, when is this matrix? What is the null space? Null space. So finding the null space of A minus lambda I. Okay, so lambda here is 0. Okay, so I get the same matrix, 9, 2, 0, 0, multiplied by some vector, x1, x2, is the 0 vector. So we're back to homework 1 situation now, where we're solving for the null space of some matrix. Is there something non-zero by which this matrix can be multiplied so that out on the other side comes 0? Is there some non-zero vector being crushed into this 0 here? So let's find that. So help me out. So what is the solution? So this is the typical AX equals B system, right? So I'm solving AX equals B, and actually A minus lambda I plays the role of our old A times X equals 0. This is what I'm solving for the null space. Okay, so we can write down the solution here. Okay, what's our standard way of writing down a solution? So what's the pivot? What's the free variable?
The pivot is 9.
The pivot is this first column with a 9 in it. So this is pivot. And this is free. So how do I write down the solution? Set the free variable to something like 1, right? If I had more free variables, I would set one free variable at a time to 1. So if I had 2 free variables, we'll see an example of this coming up. I'll set one of the free variables to 1 and the others to 0. And I'll go over, set the second free variable to 1, all the others to 0. And each time I figure out what the value of the pivot is. So if I set the free variable to 1, what's the other guy? What's the value of the free? Minus 2/9. Okay, so I could have set, okay, another x that's at any multiple. This is n eigenvector. I could have set this to 9, and this would have been minus 2, is also an eigenvector. The eigenspace, this guy, is the space generated by any one of these eigenvectors. So what is the line that's generated by this, the eigenspace? The entire eigenspace associated with 0 is all the multiples, or C is some number, of the vector, just one of these eigenvectors. Let's pick the one that's minus 2/9. That's the eigenspace associated with that eigenvalue, all the multiples. Okay, now I still have the second eigenvector, eigenvalue, and I will find a distinct eigenvector. Notice that when I have distinct roots, like here, 0 and 9, then I will have eigenvectors that point in different directions. The eigenvector that I will find now will not be on the same line as the first one that I found. It will be on the plane and it will point in a separate direction. So for the second eigenvalue, I write down the matrix A minus lambda I is going to be this matrix, 9 minus 9, 2, 0, 0 minus 9 is 0 minus 9. Okay. So this goes to this matrix. Well, that's equal to that matrix, 2, 0 minus 9. That's my A minus 9, or A minus lambda I, the null space of A minus lambda I. That is the eigenspace associated with the value 9 is going to be the vector that solves this system of equations. But yes, I do say system, but how many equations do I really have? Isn't one a multiple of the other? So if you do Gaussian elimination, you can make a 0 right here. Okay. Okay, so if you add 2/9 of this row to that row, rather if you add this row to 2/9 of this row, you'll get a 0 here. So I really have one equation, 0, 2, 0, 0 times x equals 0 vector, the 0 vector here. So what is the correct solution? What is a solution? So I'm looking for this eigenspace here. So what's the solution here? How do I write down the solution? What's the free variable? What's the pivot? Which one is free? Which one is pivot?
X2 is free.
Why is 2 free? So what's the definition of a pivot?
The pivot's the first
entry
in a row.
First non-zero entry.
Non-zero entry, yeah.
Okay.
Oh,
so so which one is the pivot then? This one, right? And this one, it's kind of odd. That's maybe the first time you see a matrix where the pivot shows up. Like the x1 ended up being a free variable, but so what? So here's free, and that's the pivot. So the solution, what's the standard way of writing down a solution? Give the free variable anything that makes it happy, or rather it makes you happy because you want a simple looking solution. But you would normally set them to 1, the free variable to 1, and the other guy is then determined. So if I set the free variable to 1, what's the other one? Has to be. Is a solution. 20, 0 is also a solution. So the eigenspace. So the eigenspace associated with 9, the eigenvalue 9, is going to be all the multiples of this vector that I found, which is a line, one-dimensional, well, a line, that is a line in R2 that lies on the plane. Okay, all these vectors lie on the plane because I have 2 by 2 matrix. Okay, so this is a bit of a review of finding the eigenvalues and eigenvectors in the 2 by 2 matrix. So notice, however, we handpicked this example because, well, there are a couple of things to notice. First of all, it's quite legitimate to have a 0 eigenvalue. Lambda being 0, there's nothing special about it, other than later we'll see that a matrix has a 0 eigenvalue if and only if its determinant is 0. That happens. But 0 is a legitimate eigenvalue. We don't allow for 0 eigenvectors. That wouldn't make sense, because if an eigenvector, if I'm solving for this, and if this is 0, then any matrix, any lambda satisfies this, because no matter what lambda is, and no matter what A is, if X is 0, this equality is satisfied. So we're not interested in this situation when X is 0. Okay, so we make our eigenvectors non-zero, but it's okay to get a 0 eigenvalue. That's fine. We have a legitimate eigenvalue of 0 here, and we have an eigenspace associated with this eigenvalue 0. And here's the eigenspace associated with the 0 is a line. Okay, all the multiples. And where's this line? If you had to draw this line, by the way, what's the eigenspace if I wanted to draw? So here's my -2, 9 vector. It's 2 units here, 9 units there. So a line that passes through this, all the multiples of this vector, this vector is 2, 9, -2, 9. All the multiples of this vector in either direction, those lie on a line. That's why we say it's a line. It's an eigenspace associated with this one. And how about if I wanted to draw the eigenspace associated with A9, E9? Can you help me draw this, please? Here's the 0, 1 vector. Let's make that purple. Oh, well, what did I get? 1, 0 vector. And here's the line, all the multiples of 1, 0. Notice that those eigenvectors, and this is an important key point, those eigenvectors point in separate directions in R2. I have 2 of them. This means that they form the so-called basis of R2. That is, they span the entire R2 plane. This means that any vector in R2, like this one, for example, can be represented as a linear combination. This vector here, if I wanted to represent this point, I can represent it as a linear combination of some of this some amount of this vector, so some amount of this vector here, maybe that much, and some amount of this vector, maybe that much. And when I add them up, I get exactly at this red point. So any point can be represented as some linear combination of these purple vectors. Those purple vectors form a basis in R2. This is an important feature, which we'll find useful by the end of today's lecture. Hopefully, we'll get there. When we'll talk about computational applications, for example, computing the powers of a matrix. And there are tons of others and tons of other applications. Okay, so, and this happened, by the way, that the eigenvectors each going in their own merry way and not being on the same line, crushed in the same line, is because we had 2 distinct and real eigenvalues. Okay, let's see another example. Any questions so far about this? Does it make sense to people?
Right? So the vectors yes. Always go in separate directions.
No, not always.
Not always.
They went. We'll see another example coming up next. Actually, well, in 2 examples. Okay, so if you do have distinct, so here's a good point. So if your eigenvalues happen to be real and distinct, they will always point in separate directions. That is correct. If they are not, then they may or may not, as we'll see. Okay, so let's see. Another example, we're going to take this matrix. A is going to be 3, 3, 8. Okay, could have picked different numbers, but this is the matrix tend to used in a different section. So here's the matrix A. This time it's 3-dimensional. It's 3 by 3 rather. So it acts on 3-dimensional vectors. So let's go through the usual procedure of, this is our second of 3 examples, startup examples today. So this is number 2. Okay, so let's find the eigenvalues and eigenvectors. So I start by writing down the characteristic equation to find the eigenvalues first. And that is the determinant of this matrix, 3 minus lambda, 3 minus lambda, 7 minus lambda. Those other entries stay put. And this determinant ends up being 3 minus lambda squared times 7 minus lambda, which is a cubic polynomial in lambda. If you expand this, the highest power of lambda is going to be lambda cubed. And that's not surprising because you had a 3 by 3 matrix. You would get a cubic polynomial for sure. This is the characteristic polynomial. And the characteristic equation is setting the polynomial to 0 to find its roots. But this one is already factored because it was a nice matrix. So I can find the roots here. It has, how many roots does it have? An nth degree polynomial will always have n roots. Now, some of those may be complex, some of those may be repeated, but you will have n roots for sure. Otherwise, Galois would be turning in his grave 200 years later. Okay, so there are n roots, and those roots are the one repeated root. Okay, lambda 1, lambda 2 is 3, so that comes from this piece. And the third root is lambda equals 7. So these are the roots of the characteristic polynomial. Okay. Now, for each one of these roots, we're going to find an associated eigenspace. So eigenspace for each lambda. Well, let's start with a simple case. Well, lambda equals 7. What do I get in that case? A minus 7 lambda is going to be 3 minus 7 here. Okay, so 3 minus 7, 3 minus 7, 7 minus 7 here. So I will end up with 4, 8, 0, 0. Okay, minus 4, 0, 0, 0, 0. Now watch what happens. Let's okay, so now what's the next step, please? How do I find? So we're looking for the eigenvector associated with this. So the eigenspace, really, the eigenspace associated with 7. So how many eigenvectors are there in this space? So what am I solving? So in other words, the null space, we're looking for what's in the null space of A minus 7I. Oh, what do I have here? People didn't stop me? All right, let's make sure people are here. Did people sign in, by the way? Everybody checked in? Okay, so let's end this check-in here. Where is this? Okay. All right, so what's in the null space of this? So I go ahead and solve the usual. I want to find what's in the null space here. So in the null space, there's going to be some vector, x1, x2, x3. Well, first let's, okay, since I wrote it down, that makes this 0, right? So that's what's in the null space of A. Can you see that there will be something other than 0 in this null space? Please help me out. Why do I know when I look at this matrix that this has a non-zero solution? That is, there's something non-zero in the null space of this matrix. This matrix is A minus 7I. Why do I know that there is something non-zero? Can somebody help me out with this, please?
Because we have at least one free variable.
Exactly, thank you. Because we have at least one free variable. Okay, by the way, how many exactly do we have here this time?
Is an x3 the free variable?
X3 is the free variable. This column is free, and these guys are pivots. Okay, because why? Because I have zeros right below them. This time, it's not varices. I have a step-like form, so it is already in row echelon form. Now, the Gauss-Jordan elimination brings it to an identity, to a reduced echelon, row-reduced echelon form, meaning it does one more step by doing what? Can you remind me? Let's do it just for practice. We don't have to do it. We'll here to write down the solution, but let's do it because just for practice. What's the next step in, what am I trying to do in the Gauss-Jordan elimination next?
We can either make the pivots 1 or they make the 8 a 0.
Yes, that's exactly right. I can start with either one, but I'm trying to get a ones there, so I could do either one. So row reductions take me to first. Let's add to. Okay, so let's write down row 1 plus twice row 2 first. I could have scaled them, but let's do it that way. So I get minus 4, 0, 0. Now I get here, I'm leaving this row alone. The third row, I can probably not even rewrite, but let's write down the row, these zeros. Okay. This scaling, and I'm going to combine the two steps now. Just multiply both rows by minus 4. So I get this.
Minus 1 over 4.
Yeah, by minus 1 over 4. Thank you very much. And I get exactly this matrix, right? Everybody on the same page, right? Okay, so solution for this. What's the solution? The usual way of, so I have one free variable. So what do I do with the free variable?
Give values.
Yes. So this one is going to be the free one, free. So I set that one to 1, right? And I set the other guys will then have to be 0. right? So the eigenspace associated with 7, this is the eigenvector we found for the eigenvalue 7, is all the multiples of this vector. This is a vector in the three-dimensional space in R3. This is a vector in R3. Okay, so if you want to draw R3 real quick, so let's say if it's the x-axis, the first axis, let's say this is y, this is z, then this is this line here. This line in both directions is the eigenspace associated with 7. Okay, all the multiples of, oh my God, z, let me renumber. So it's the third component here. So let's make this x. Okay, it's slightly rotated and flipped space, but the z component, so everything on the z component, that's the eigenspace. Okay, so I can, all right. So now let's find, so where are we? So we had 3 eigenvalues, 3 was one repeated eigenvalue, and 7. For the eigenvalue 7, we found the associated eigenspace. Now the next is lambda 1, 2, the 2 roots, which were both equal to 3. We'll find the associated eigenspace. So I'm going to have a minus 3i is going to be what? So here's my matrix, original matrix, so that you remember, here it is up there. So a minus 3i is going to be, oh no, that's not that matrix. The original matrix, 3's there. You see, remember this matrix? That's what we are dealing with. The original matrix had 3's there. 3, 3, and here you had a 7. If you remember, that's the 7 there. So this is the original matrix A. So so let me copy this so that I don't copy the wrong thing later for the next slide. Okay, so a minus 3i is going to be what? 0, 8,
0, 8, 0,
0, 8, 0,
0, 0, 0,
0, 0, 0,
0, 0, 4.
0, 0, 4. Okay, so great. Okay, so by the way, this is the interesting case. Like in our third example, I'm jumping ahead for 1 second. In the third example, I'll change one entry in this matrix and we'll get completely different results. But the computations we won't have to redo too much of them because we're doing them now. So here's my a minus 3i. So what are the pivots? What are the free variables? Okay, so that, yes, please.
Free is the x1.
So x1 is free. And those guys are the pivots. Okay, I have 2 pivots. Again, I have 2 pivots, 1 free. So the null space associated with this root, repeated root. So let me, for a second here, an important side note. Definition. The number of times a root appears in the characteristic polynomial appears in the characteristic polynomial. Is called the algebraic multiplicity of the root. Okay, so this is one of our 2 key definitions of today. So what's the algebraic multiplicity of 3? So characteristic polynomial was lambda minus 3 squared, lambda minus 7, right? That was the characteristic polynomial, or 7 minus lambda. Okay, let's write down correctly. 3 minus lambda, that wouldn't make a difference to 7 minus lambda, was the characteristic polynomial. It's a 3rd degree polynomial, has 3 roots. One of them is repeated. The number of times that lambda, which one is repeated? Lambda equals 3 is repeated. What's its algebraic multiplicity according to this definition?
3.
Sorry?
Is it 3 or 2?
No, it's 2, right? It's 2. The algebraic multiplicity of 3 is 2. 3 just happens to be the value of the eigenvalue itself. Okay,
not of lambda in general, but the root itself.
Yeah, number of times. Okay. Yeah, okay. So lambda appears, that's correct. The root root lambda I appears is called the algebraic multiplicity of the solution, that lambda I. Okay, so for example, lambda equals 3 has multiplicity 2 because it appears here 2 times as a root of a characteristic. Does that make sense to people what that means? Okay, so now let's write them down the eigenspace associated with the roots of algebraic multiplicity 2. Okay, so eigenspace for 3, lambda equals 3. Repeated lambda. Okay, so what is that? So help me out now. Okay, what do you do? Like if somebody asks you for the null space of this matrix, what's in the null space of this matrix?
We're going to give a value to the free variable, x3, to x1, sorry.
Yes, x1 set to 1.
1.
Okay.
And the other ones have to be 0.
And the other ones have to be 0. So this vector, x, does everybody see this? That I have a one-dimensional subspace. Notice this is an interesting case in that I have a root that repeats. This doesn't have to be the case. I could have found, if I had 2 free variables in this matrix, in A minus 3i, if I had 2 roots, 2 free variables, then I would have 2 linearly in the null space. I would have, now the null space of A minus 3i would be 2-dimensional. And I would have 2 independent vectors pointing in their own directions. But in this case, I do not have that situation. I have a root of algebraic multiplicity 2, and the eigenspace associated with it, how many dimensional is it? So key to this, we're doing this through examples, so that and I'll give you definitions as we go along. E3 is what's the dimension?
1.
Yes, is 1. The dimension of the eigenspace associated with an eigenvalue is called the geometric multiplicity of the eigenvalue. Definition 2. Definition 2. This was definition 1. Okay, we have 2 key definitions of today. The geometric multiplicity of lambda is the dimension, the number of linearly independent vectors in its null space, dimension of the eigenspace associated with lambda. Okay, so what's the geometric multiplicity of this? Lambda equals 3. It's the geometric multiplicity of this. It's a line, right? It's a line. It's a one-dimensional line. All the multiples of 1, 0, 0 vector is a line, the x-axis in the 3-dimensional R3. It's a line in R3. Line in R3. That's the eigenspace. The eigenspace has 1 dimension. It's a line. So the geometric multiplicity is 1. So let's do a brief recap. We start out with a 3x3 matrix. We compute its characteristic polynomial. The characteristic polynomial will have 3 roots, but some of these roots may be repeated. In this example, we had 3 roots. One of those roots, lambda equals 3, was repeated. It appeared in the characteristic polynomial with degree 2. This means, by our definition, that the algebraic multiplicity of that lambda is 2. With each lambda, I have an associated eigenspace. The dimension of that eigenspace, which is the number of linearly independent vectors that I can find in the null space of A minus lambda. Okay. The dimension of the eigenspace is, as we saw, can be smaller than the algebraic multiplicity of an eigenvalue. In this case, the geometric multiplicity of the eigenvalue 3 was 1, and the algebraic multiplicity of lambda equals 3 was 2. Does that make sense so far? So far, so good. We're halfway through the story. So now let's move on. Now what we're going to do, I'm just going to do our third example. So this is going to be our third example with A, where A, remember this matrix from the example that we just did? I'm just going to change one entry right there. I'm going to make this matrix even simpler. I'm going to put a 0 there. What happens now? You help me out with this. So it's very, very similar. The routine is the same. So step one. So find eigenstuff. So the problem we're facing is find the eigenstuff of this A. So the first step you've suggested was to find the eigenvalues of A. Let's find the eigenvalues of A. This shouldn't be too much trouble. Determinant of A minus lambda I, old story. I'm writing down the same old characteristic polynomial. Okay, what's the characteristic polynomial? So same old determinant of this. And that ends up being 3 minus lambda squared, 7 minus lambda. Is this any different from what we had last time? Do I have different roots? 7 minus lambda equals 0 has, this is the characteristic equation now, solving for the roots to find the eigenvalues, has roots. Same thing, same story. 2 repeated roots, both equal to 3, and the third root equal to 7. So these are the eigenvalues. Found them, just as before. Eigenvalues. Nothing new. Now, step 2 is to find eigenvectors. Now, find the eigenspace associated with 3 and the eigenspace associated with 7. For 7, there's really no, is there a change for 7? Okay, let's start with lambda equals 7.
Again, we have one free variable and 2 pivots, same thing.
Okay, yes, A minus 7i is going to be, what's going to be A minus 7i? It's going to be minus 4, 0. And this time, okay, this 0 here is important. That's our new matrix. Let me copy that one so that we don't paste the wrong thing. Okay, so now our matrix is this. Again, I have, this guy had algebraic multiplicity 1, the root lambda equals 7. And what's the eigenspace associated with it? In a moment, we'll claim that the geometric multiplicity of a root, there's no way it can be greater than the algebraic multiplicity of it. That's what we'll claim in a minute. But for now, what's the eigenspace? What's the null space? Null space, how many vectors do I find in the null space of A minus 7i? Because that's the eigenspace associated with 7, with lambda equals 7. So what's there in that null space?
0, 0, 1.
0, 0, 0,
vectors.
0, 0. Oh, exactly. That's what I was asking. So this is this. All the multiples of this is E7. So we found E7. It's one-dimensional. It's still a line. Now let's see what happens for lambda for the repeated root.
Now we have 2 free variables. And one pivot.
Yes. So A minus 3i is going to be 0, right? So I'm subtracting lambda. Here's my A. I'm writing down A minus 3i. So off the diagonal, 3's go. 3's go off this diagonal. And I have just one non-zero entry in the entire matrix. So what's the free variable and what's the pivot?
Should that not be a 4?
Sorry, one more time, please.
Should that 7 be a 4?
Oh, yeah, yes. The one non-zero entry here. Okay, so which one is the pivot? Thank you. The pivot, and which ones are, huh?
X3 is the pivot.
X3 is the pivot. And these guys, now I have free variables. Before I had just one free variable. And as you've told us, now I have two, right? That's what you told us, right? So we have two free variables. Okay, so here's the important point. So what's the dimension of the null space? So what is the dimension of A minus 3i, which by the definition we just gave, by new definition, equals geometric multiplicity of lambda equals 3. That's our eigenvalue, for which we have new by notation, notation is the dimension of the eigenspace associated with the eigenvalue 3, right? Okay, so let's write down, because I have two free variables, help me out. How did we write down solutions to ax equals b? Ax equals 0. Actually, that reminds me, we have to do a review problem on ax equals b today. That's why I would postpone the homework assigned due date so that I do one proper ax equals b problem. It's completely written down with a complete solution so that there are no questions. Okay, so but back to this problem. Here we're solving for the null space. We're solving ax equals 0 here. Okay, so how do we set, what's our standard procedure? Please remind me. So now I know that my null space is going to be two-dimensional. Okay, so I have these pivots. I have this free, and this guy is going to be free. This means that I set them to 1, 0, and 0, 1 here, and figure out in each case, I figure out what the pivot is. Okay, so what is the pivot going to be in each case? In both cases, I get a 0 for the pivot, right? The pivot has to be 0. If I plug it back into the matrix, I get that the pivot is 0. Okay, it's a simple matrix. So what's the complete solution? Complete solution. So how do I write down all the vectors in the null space of A minus lambda I? Some multiples of these two vectors. Right? In the linear systems part, you used the variable names, like you've used x1 and x2 here. But yes, you can write it down that way if you'd like. But it's all possible multiples of these vectors. What do these vectors form in the three-dimensional space?
By themselves, they form a line, but the addition of those two lines, it has a
exactly. Yes, that's exactly what you said. So let me see. Let me try to draw it, and you tell me if that's what you meant. So each one of them by themselves, okay, so it's some vector, like the first guy is a vector. It actually like in the x direction, but I draw it upwards. So in general, it will be some vector somewhere. Okay, this guy is, in this particular case, the guy is in the y direction, just the y-axis, but let's say in general, it's some vector in some direction. So by themselves, they form a line. But I'm taking the sum of their multiples, all possible sums. So a vector, for example, like this, okay, can be represented as some number of times this vector, some number of times that vector. You add them up. So you get to any vector on that plane. This is a plane in the three-dimensional R3 is a plane in R3. Right? This is a plane, this is a two-dimensional plane. Now let's recap a little bit. Let's write down the morale of the story. So what did we have? So any questions about this? So what we did, we found that the eigensuff, this is the eigenplane, this plane is a plane, is the eigenspace E associated with 3. This plane is the eigenspace, lies in the 3D case. Well, right. Okay. Any questions about what we did? Let's recap for a moment. Let me recap for a moment. So here's what we had. In example 2, we had this matrix with an 8 here. In example 3, we had this matrix here with a 0. both have the same characteristic polynomial. Same 3 minus lambda squared times 7 minus lambda. The characteristic polynomial is the same for both. The characteristic polynomial. Roots, the same. Roots. Lambda 1 equals 3, lambda 2 equals 3, and lambda 3 equals 7. In both of these cases, right? The same roots. So algebraic multiplicity, the algebraic multiplicity of 3, what was the algebraic multiplicity of 3? Help me out, forgot the definition.
Two.
Is 2 here, and is 2 here. The geometric multiplicity of this eigenvalue is, what was the geometric multiplicity in the first case?
One.
In this case, it was 1. And in this case,
2.
It was 2. Now I want to draw a picture in general, what's happening. Suppose you have, in general, so first let me tell you the result. In general, the algebraic multiplicity of an eigenvalue is always as much or bigger than the geometric multiplicity, as is the case in this example. So the geometric multiplicity is at most the algebraic multiplicity of an eigenvalue. Okay, we'll argue that a little bit more generally, but we won't give a proof, but we can give a compelling enough argument that is just one little step away from like full-blown proof. Okay. So let's a key result. Let's write this down. Key result, and I'll draw another picture in a minute. Key result, okay, is that the geometric multiplicity of lambda and the algebraic multiplicity of lambda are related like this for any lambda, any root of the polynomial. The geometric multiplicity is at most the algebraic multiplicity. The nice case, which we're interested in computation applications in general, case is when the geometric multiplicities and the algebraic multiplicities are equal. When that happens, you will be able to find n in Rn. So you start out with an n by n matrix. When this happens, you will have a basis of eigenvectors in the entire Rn. So eigenvectors themselves, the n eigenvectors of the original matrix A, will be linearly independent. And as we'll see in a few minutes, that is huge help in applications. For example, in computing today, the one application that we'll consider is computing the powers of A, or decomposing the matrix. So we'll talk about matrix decomposition next. And this is where this will be important. So the nice case is when you have n independent eigenvectors. So linearly independent is always in Rn. So these are all vectors in Rn. These are n-dimensional case. Then notice what happens if you write down these eigenvectors in a matrix. What would be the dimensions of this matrix, by the way? So I'm writing down, here's a matrix. We're going to call this matrix S, by the way. I can write down n independent eigenvectors, all the vectors, the columns in a matrix, and call that matrix S, just to give it a name. If all these eigenvectors are independent, which will happen when the geometric multiplicities and the algebraic multiplicities are equal for each of the roots, that will happen. And by the way, can I ask you this? What if I earlier made a little bit of a big deal about the case of the eigenvalues, the real eigenvalues being distinct? If all the eigenvalues are distinct, can you help me out? Like what happens? What's the algebraic multiplicity, first of all, of each root?
Would it be 1?
1. So I have n of them, and each has an algebraic multiplicity 1. So by the way, the algebraic multiplicities always sum up to n. In this case, 1, 1, 1, 1, 1, they all sum up to n. What's the geometric multiplicity of each one? So I just claimed the geometric multiplicity can never be larger than the algebraic multiplicity. So what would be the geometric multiplicities of these roots, each having an algebraic multiplicity of 1?
If it can't be bigger than 1, so it has to be 1 or 0?
It has to be exactly, that's what I was asking. It has to be 1 or 0. But I claim that we can rule out the possibility that the geometric multiplicity is 0. Why can I rule this out? If I rule this out, what we have is that the geometric multiplicities are 1 and the algebraic multiplicities are 1. So we have n, by the way, the eigenvectors in each of these eigenspaces associated with these eigenvalues, this is easy to show, are linearly independent themselves. Then I will have n linearly independent eigenvectors. In which case, this matrix that I just wrote down here will have n linearly independent columns. Can I ask you if this matrix is invertible? Remember our discussion about invertibility? What does it mean for the columns to be independent? You do Gaussian elimination, you don't get the row of zeros. That's when you can invert a matrix, remember? So all this numerical stuff is in the homework. You do Gaussian elimination, the homework question says just invert this matrix. You do good chug along with the Gaussian elimination, you don't find a row of zeros, that matrix is invertible. If you find a row of zeros, that's not invertible. And you find a row of columns after Gaussian elimination. If those rows, or equivalently columns, are multiples of one another. Okay, that means you have fewer pivots than you have rows. Then you have a row of zeros. Does that make sense? Okay, so this matrix will then be invertible, but I kind of like glossed over the fact that the geometric multiplicities cannot be zeros. Why can the geometric multiplicity not be 0? Can somebody help me argue with this? Argue this?
Would that just be the 0 vector?
Sorry, one more time.
If the geometric multiplicity is based off the dimensions, if it has 0, wouldn't that just be a 0 vector? Or the 0?
Actually, you are correct, but I still want to nitpick though. You are correct.
Can it be just a single point?
Yes, the a minus lambda, I guess both of you said the same thing, right? That a minus lambda I has to have a non-zero solution. The eigenspace has to be at least a line. If it's not a line, if it's something smaller and it's just like a 0 vector, then that means that that would mean that a minus lambda I would be invertible, would have only 0 in its null space, which is not good. It should not happen. That's how you select lambda, so that there is something non-zero in the null space, right? Does that make sense? So notice how nice this case is. I mean, we don't know why it's nice yet, but at least the observation we can make that if the eigenvalues are distinct, then the geometric multiplicities add up to the entire n. I have n distinct, pointing in their own merry ways, that is linearly independent, n linearly independent eigenvectors. And if I put them into the columns of this matrix S, that S will be invertible. And next time we'll see why the invertibility of S is such a desirable thing to have. Final picture before I go. So here, suppose you have roots of characteristic polynomial, like lambdas are, let's say 337 could be, or just some other 448 or something. Okay, so I have 3 roots. There are 2 possibilities. 2 possibilities can happen. 2 possibilities. I have a slide about this somewhere. 2 possibilities that can happen. Two possibilities. Okay, so there's no picture. I'll insert the picture in the notes. I'll tell you more about the notes, by the way. Okay, so you have this one. Okay, 3, 5, 5. So you have 1 repeated root. There's only 2 possibilities can arise. Either the geometric multiplicity of this 5 is also 2, right? It can never be 3. It can never be larger than the algebraic multiplicity. Algebraic multiplicity of 5 is equal to 2. Okay, this one is just a lonely guy, 3. So let's draw the three-dimensional space like that. This time, let's make X here, Y there, Z there. Okay. So if the geometric multiplicity is 2, then I have a plane associated, goes through the origin, by the way, because it's a space, subspace. 0 is always the solution to A minus lambda I. So I have this E5. This is my E5. Notice that because it's a plane, how did I get to that plane? I found these two purple vectors that were in the null space. Now they point in separate directions. In the null space, no, so this is the null space of A minus 5I. The plane is the null space of A minus 5I. And I found it to be a plane because I found these two lines, as you said, by themselves, they were lines, right? And then I picked a representative vector on each line. So these are the purple vectors on each line. So anything on the plane can be given by these two vectors. And then associated with this, let's make this guy green, with this 3, I have a separate line associated with E3, right? It has its own vector. And the point is, we actually haven't proved this, but it's easy to show that this green line will never be on that plane. That's associated with the other eigenvalues. So that guy juts out in its own direction. So what will happen is that this set of vectors will be independent.
Don't they form a parallelepiped altogether?
Yeah, so you can build a parallelepiped there. But the point we're trying to make, that this set of vectors, this set that I just drew, these are vectors pointing every which way in R3. So in R3, independent. If I put those vectors in the columns of S, that S will be invertible. But what happens here if the dimension is 1? Then the picture looks a little bit different. So here's my Y, here's my X, here's my Z, and here's still my line there. So E3 is still there. It has its own vector, it's pointing that way. But then instead of a plane, as we had in the example number 2 of today, the purple E5 is going to have just one vector in the null space, not two independent ones, but just one vector in E5. So the set of eigenvectors, this is the set of eigenvectors. My set of eigenvectors then looks like this. Well, I only have 2 elements in that set. It looks like this. Just 2 vectors there. Okay, and those 2 vectors, set of eigenvectors, just 2 of them, do not form a basis in R3. There is no way any 2 vectors you take in R3, they're going to lie on their own line. Like if you consider that line in which the green and the purple vectors lie, that's just a plane in R3. There's no way any vector that's jutting out of that plane, there's no way to represent that vector as a linear combination of the purple and the green vectors. So they do not form a basis in R3. I do not have 3 linearly independent eigenvectors in that case. And this is okay, so this is considered bad. And this is considered good. Good, again, and next time we'll see why. Good is the case when I have n linearly independent eigenvectors for a matrix that's n by n. And as we just argued a few minutes ago, that will always happen if the roots are distinct. But if they are not distinct, like we had the repeated root with lambda equals 3, then it may happen, may not happen. Then you can have either this picture or that picture if you have repeated roots. And with the repeated roots, you want this picture, good. Distinct roots, also good. This picture, good. This picture, not good. This picture, not good. Okay. We're running out of time. Now I want to do an AX equals B system. If you have any questions, please stop me. I'm going to pick a small example, which it turns out is taken from your homework, but that's okay. So here's the example that I took from Canvas, and then it ended up being a homework question, but that's okay. So here's a 2, 6 is the matrix A, that's my A. times x, you're asked to solve a question like this, equals the right-hand side is 3 minus 1. This is a typical AX equals B system. How do you solve it? Solve it. Steps. Find a particular solution. What is a particular solution? Solution. Okay, so let me just be clear. First, you do Gaussian elimination. So steps I'm going to keep on the right side here. Let's insert one more just in case. So steps we can fit here. But the Gaussian elimination, let's make this smaller so we can fit Gaussian elimination on it. Okay, so help me out. Help me do Gaussian elimination on this. What do? You write down the matrix in its augmented form, right? So you put this guy on this side. It's just the way it's done. Okay. And you do Gaussian elimination on it. So when you add like a third of row 2 plus third of row 1, when you add that. So I'm not changing the first row, let's say. I could have switched the rows, would have been easier, but that's okay. So let's say you leave the first row unchanged, and to the second row, you add a third of the first row. What do you get here? Do you get this?
It's minus 1/2.
Oh, minus 1/2. Yeah. Do you get this? Do we get this? Okay. Now I want to find a particular solution. Notice it's kind of confusing maybe at first. There are special. So okay, what are the special solutions? Help me out. In what context did we use the term special solutions? So the special solutions were the solutions to AX equals 0, and we'll need those here. So I'll write down special solutions also. But a particular solution is the one that solves AX equals B, the simplest one you can find. There are millions of them, infinite number, in fact. But you can pick one simply by setting, let's say, free variables to 0 this time, free variables to 0. Because that's easy. So what do I get if I said, what's the free variable, by the way?
X2.
X2, this is free, right? Free. And this guy is the pivot. So if you set the free variables to 0, what do I get?
1 or x1 is equal to negative 1/2.
Yeah, x1 is negative 1/2, and the other guy is 0. This is a particular solution. So x particular. So x particular is that. Okay, we found an easy, so pick a simple one, any one. Found a particular solution. Just that vector solves this problem. It solves this problem. We just found one solution to AX equals B. That is a solution. No doubt about it. We just found it. 2, find the special solutions. What are the special solutions? The ones that null space, in other words, special solutions, we'll call them the null space of A. You find the null space. Which ones make AX equals 0? So you solve AX equals 0 as well. Find the null space. Space of A. So this one, that's step number 2. Okay, so what's step number 2? Let me make this smaller. Maybe I can fit the whole thing on this little slide. Okay, so this was finding, so this was particular. Particular is this guy. Now I want to find null space. For the null space, it's the same matrix that I have, right? It's the same matrix here. It's just the right-hand sides are 0. So that's the case where so 1, 3. So let me write down the whole thing just to be clear that everyone's on the same page. 0s on the sides. I would normally didn't even write down anything to the right of the vertical bar because those are 0s. Now, no matter what you do with the rows, with the elementary row operations, right? You still get to the same thing, minus 1/2, and I'm not writing down the 0s. So after Gaussian, This is Gaussian, the row operations, whatever. Gaussian gives this. So now I'm looking for special solutions. So what it, 0. The right-hand side is 0. It's the whole point of the special solution. Special solutions solve for the null space, as if B wasn't even there. Those are the special solutions. What's in the null space? All right, so how do we write down the null space? X special. In this case, what's the dimension of the null space?
2.
The null space.
Wait.
One.
Oh, sorry, 1.
Right?
Sorry.
Yeah, that's the number of free variables, right? So the null space has the dimensions as many as free variables that I have. In this case, it just happens to be 1. I have one pivot. This guy is the pivot, and the other is free. So the special solution, what you set the free variables one at a time, right? So set this free to 1. Let's make that purple for free. Okay. So that guy was free. If I had more than 1, then I would set them 1, 0, 0, 1, as we did in the Eigen example. And the other guy works out to be what then?
3. -3.
-3. -3. Right? So that's the special solution. 3, add them up. Just write down the complete solution, right? The complete solution. Why do you get to add them up? So help me out argue this. We have 1 minute left. Write the complete solution, And that's the answer to AX equals B. When you're asked, what is AX equals B? X complete is X particular plus the null space. In this case, the special solutions, specials. Why does this work? Because if AX particular equals B, and if AX special equals 0, when you add them up, here, what do you get on this side? You get AXP plus AX special. If you take A out of the brackets, you get X particular plus X special. And here you add B to 0 and you get, so this is the sum. Okay, this is a bit of a shorthand, but it should be clear. So this piece is the solution, Okay, so in this case, what is the solution? So here, X complete, the final answer. So here, answer. X complete is going to be the particular solution, which was -1/2, 0, plus what's in the special? All the multiples. The null space is an entire line. So that's how I write down the line of solutions there. Okay, and again, some people use the free variable name here. X2 was our free, so use X2. Use C, whatever, just as long as you say that it's some multiple. Okay, so this is the final answer. Any questions? So we should be clear, right? Then it's okay. So this is we ran out of time, so we'll stop here because I have another section. But let me tell you. So please stay current. I'll post today's notes as well there. So you've seen these new notes posted. This is going to be by the end of this week. I'll try to keep it short, but it'll probably end up like about 60 pages or so, right? But it's like large print. It's a bunch of examples. It's not a dense read or anything. So that will be your guide to the final. So with all the examples you work through with the examples and everything. So what will end up happening is that we don't have too much time to cover the applications that I wanted to cover in the linear algebra piece. So there's plenty we could have done. But we've done the bulk of it. We've done the core of it, the math of it we've done. So next time we'll talk about matrix diagonalization. And Monday will end up being a recitation essentially. So I'll do a bunch of problems. So like before, I thought maybe the last day we'll have enough time to kind of take it easy. I'd come in, you'd ask me questions, but this time we don't have that luxury. So I'll come in and do a bunch of examples on Monday. So that's your prep for the final. So we still have one new piece of material to cover. Okay, so now we have to wrap up. Any quick questions?
Is there a quiz? Is there a quiz on Wednesday?
There is a quiz. And what's going to be on the quiz, by the way? Can somebody predict? And I'll tell you if it's right or wrong.
Up to eigenvalues.
Yeah, there will be a basic question on eigenvalues. Okay, and there will be something like, sorry?
All right, never mind.
Yeah, maybe, well, yeah, I didn't hear it, but if you said like something inverting a matrix or something, we didn't have those questions yet, right? So probably something like do Gaussian elimination to invert a matrix or something like that. Okay, so one question about that and one question about like 2 or 3 questions and one question about the eigenvalues. Okay, so that's it for the quiz. And again, we're not done yet. We have still something to cover on Friday, and then Monday and Friday we're done. And then we'll have.
How about the homework that's due tomorrow?
Okay, so
yeah, the 3A.
3A, right? So you know what we'll do? I'll postpone this homework as much as I don't want to keep postponing. We'll postpone like 5 homeworks, maybe not 5, but a few. So I'll postpone that one because I want to talk about this at the recitation, right? So you want to cover some of the related stuff at the recitation. And then I'll talk more about it on Monday as well. But that 3A, I'll postpone it. But meanwhile, like most of those questions you can do, If you like hit a snag somewhere, right? So that's why I'm postponing it, maybe for 1 or 2 questions that we can clarify later. Otherwise, you can do most of it. So please do, you have like, I've reset, I think you have 7 attempts now. So just work on it. It's not a matter. So I want you to get all the points. That's not the point. Like I'll reset the number of attempts as long as you work on it. You get your full points, but you study for it, and then you'll be ready for the final. Okay, so actually let's stop recording. I'll edit this video, I guess, remove